There is a real dead star so close to a black hole that one full orbit takes less time than your lunch break. And the reason it still exists may be even more disturbing than the black hole itself. This system is an ultracompact binary, a white dwarf, the burned-out core of a star like our sun, circling what astronomers think is a black hole in just 28.2 minutes. It matters because the orbit is so extreme that space-time itself is stealing energy from the system. Gravity is not just holding it together, gravity is slowly erasing it. And that, to me, is the unsettling part. We usually imagine destruction in the universe as something violent and obvious. An explosion, a collision, a star getting ripped apart in one dramatic moment. But some of the deepest forms of annihilation are quiet, rhythmic, precise, almost mechanical. As if the cosmos can grind a world down by patience alone. Astronomers have been studying a system called MAXI J1659-152, one of the shortest period black hole candidate binaries ever found, first flagged in 2010 by the MAXI instrument and SWIFT. The compact object is estimated at roughly 5 to 7 solar masses in several studies, while the visible companion in earlier interpretations appeared to be a low-mass star. But the newer ultra-compact interpretation pushes the idea into something even darker. A stripped, degenerate remnant surviving in an orbit so tight, it behaves like a preview of cosmic disposal. Why would astronomers think that? Because ordinary stars do not fit comfortably in an orbit like this. A period under half an hour demands absurd proximity. In systems this compact, the companion can be hydrogen poor, partially stripped, or fully degenerate. A white dwarf makes the nightmare make sense. Dense enough to survive. Dense enough to keep losing. Imagine compressing something with roughly the mass of the sun into an object about the size of Earth. That is a white dwarf. Now, put it next to a black hole and force it to loop around every 28 minutes. The distance is so small that if a planet tried to exist there, the story would end before geology even mattered. This is where the real mechanism begins. Not with a jump scare, with Einstein. In 1916, general relativity predicted gravitational waves, ripples in space-time produced when massive objects accelerate. In 2015, LIGO detected them directly for the first time. In an ultra-compact binary, those ripples are not a one-time event. They are a leak, a constant tax paid in orbital energy. Every circuit costs something. So the white dwarf does not simply orbit the black hole. It spirals, maybe slowly on human timescales, but inexorably on cosmic ones. The orbit tightens. Tidal stress rises. Matter can be pulled away. Heat builds in an accretion flow. And if the star crosses the wrong limit, it stops being a star in any meaningful sense. It becomes fuel. There is a number here that captures the absurdity. For a circular orbit lasting 28.2 minutes around a black hole of several solar masses, the separation is only a few 100,000 kilometers, on the order of the Earth-Moon distance or less depending on the exact masses. Think about that. A dead stellar core and a black hole locked together on a track you could almost compare to our moon's distance. Except one lap takes under half an hour. You can barely make coffee in that time. And personally, that scale is what makes this feel real. Space becomes easier to dismiss when it is all light years and abstractions. But once you realize this whole death dance can happen across a distance with a human analogy, it stops feeling like astronomy trivia. It feels like a machine. There is another layer. In ultracompact systems, the star can be forced to live at the edge of Roche-lobe overflow. That means the black hole's gravity distorts the dwarf until material spills away. Not in one cinematic gulp, but stream by stream, orbit by orbit. What survives is not safe. It is being processed. And that changes the meaning of survival. If the white dwarf is still there, that does not mean it is winning. It may mean the geometry is temporarily stable enough for the destruction to continue efficiently. The star's continued existence is not mercy. It is the mechanism. In 2023 and 2024, astronomers kept refining models of ultra-compact binaries and compact object populations using X-ray timing, optical follow-up, and gravitational wave expectations for future observatories like LISA, planned by ESA and NASA for the 2030s. Systems with minute-scale periods are especially valuable because they sit near the frontier, where stellar evolution, relativity, and tidal physics collide. That is the why now. We are entering an era where we may not just infer these graveyards from light. We may hear them through space-time itself. A system like this is not only an object, it is a rehearsal for future gravitational wave astronomy in the millihertz band. The universe has been writing this signal for millions of years. We are only just learning how to listen. So, let me ask you something. Which is more terrifying to you? A star being destroyed in one violent moment? Or a dead star being slowly drained orbit after orbit by gravity itself? Put your choice in the comments before we go further. Because the deeper idea here is bigger than one strange binary. This may be one of the clearest previews we have of how the universe erases worlds without needing a supernova, without needing a direct collision, without needing spectacle. Just enough gravity, just enough time. And yes, I know world is a loaded word here. A white dwarf is not a living planet. But if you strip away chemistry and oceans and weather, what is a world at its most basic level? A coherent body of matter trying to remain itself. This system shows how even that can fail. The old picture of the universe is that danger comes from impact. A rock hits a planet. A star explodes. A galaxy collides. But some of the most final endings are gradual. Entropy with choreography. Ruin with orbital precision. And I think that matters because it humbles our instinct to look only for dramatic endings. But wait. There is a detail almost nobody talks about. The black hole may not be the most revealing part of this system at all. The white dwarf is. Because if astronomers are right, then the object that looks weaker is actually the archive. Its composition, its survival limit, And the way it loses matter can tell us what kind of star existed before this death spiral ever began. In other words, this is not just annihilation. It is forensic annihilation. A cosmic crime scene where the victim is still orbiting the weapon. Can you imagine what that means for astronomy? We are not only watching destruction, we are reading biography out of debris. A hydrogen-poor spectrum, an orbital period this short, an X-ray rhythm this regular. These are clues.
They tell us the system was squeezed, stripped, and reassembled by time. The final orbit remembers the whole story.
This is why ultracompact binaries fascinate astronomers. They connect stellar evolution to the most extreme endpoints. Research on AMCVN systems, black hole candidates with minute scale periods, and compact binaries more broadly suggests these objects can form through common envelope evolution, massive mass loss, and relentless orbital decay. It is messy. It is rare, and it creates environments where matter exists one step away from disassembly. I think that is the real payoff. Not just that a dead star can orbit a black hole every 28 minutes, not even that gravity can act like a slow grinder.
The deeper lesson is that the universe does not merely destroy, it refines, strips, and sorts. It removes everything that cannot survive the equation. What remains is not random. It is the residue of endurance.
If that idea hit you as hard as it hit me when I realized this orbit is shorter than a lunch break, leave a like. Just that fact alone deserves to be remembered. And the last piece makes it even heavier. Because one day, systems like this may vanish beneath our instruments. Not because they were unimportant, but because they completed the process. The white dwarf loses more mass. The orbit changes again. The signal shifts. The visible trace fades. What looked like a stable binary turns out to be a phase.
A brief phase by cosmic standards, in a much longer sentence of erasure.
And I cannot help thinking about how often the universe works this way. Galaxies consume smaller galaxies. Stars peel atmospheres from planets. Black holes shred the leftovers. Nothing needs to hate a world to erase it. Physics is enough. That may be the coldest truth astronomy ever teaches. So when astronomers point at this ultra-compact graveyard, they are not just showing us an exotic object. They are showing us a rule. Under enough pressure, matter stops being a place and becomes a resource. A white dwarf stops being the memory of a star and becomes the next meal in a gravitational system too deep to escape. A dead star. A black hole.
28 minutes.
That is all it takes to turn an orbit into an execution method written by relativity. If the universe feels bigger, stranger, and a little more unsettling after this, subscribe. This channel is for people who want to look at the cosmos long enough to see what it is really doing.